is that you... Let me say thank you all for coming to the last presentation of the semester for the, I'm sorry, did somebody want to say it? Technology, cybersecurity, and policy. Look, you've been saying it now for 15 weeks, and if you can't remember things after 15 weeks, technology, cybersecurity, and policy.
Technology, cybersecurity, and policy.
And of course, you're really speaking for all of the students who are not here, because they're also going to do the homework, etc. But our first speaker is Rex Laceby, and he's going to talk a bit about National Security Innovation Network, and he's going to talk about opportunities. Our main speaker for today is Dr. Keith Gremban, and he is well, I'll introduce him after Rex is done. So please, 5 minutes for Rex Laceby, and then 45, 50 minutes for etc. And so please, is the microphone on?
Oh, it is.
Okay, great. So Rex, please start. And if you could move sort of to the center of the technology, cybersecurity, policy, everybody.
Hello, everyone. Can you guys hear me?
Yes.
Yep. Yes.
Test, test. So I work at the University of Colorado Boulder. I'm attached to TCP, but my other boss, not Dan Massey, is the Undersecretary of Defense. I am a retired Marine. I was in the Marine Corps for 21 years, a lot of trips to Iraq and Afghanistan, and we call that the pointy end of the Department of Defense. And our job was to keep you guys safe, to do interoperability exercises, to train partner nations, to do humanitarian operations. And my job now is to use your ability to think outside the box and the programs we run here at CU Boulder and our makerspace like just down the road or the Idea Forge or the BTU to let U.S. military units combined with the innovative spirit of our local ecosystem and the ideas that you're just going to think of that me as a crusty captain or an old contractor like Keith here are not going to think of. So Ensign is a great organization to try to help develop communities of innovation to solve national security problems. And we have a new program that we started last year called XForce, and XForce Fellowship program and the remote program are some amazing opportunities that I would love to get every single buff at these internships. As I said, fellowship, but it's pretty much like an internship. I'm a CU grad. I love being a buff. I love being able to help young men and women like yourselves, not just do something for the government, but try to get you guys a better scope. Some of you might want to do something for the Pentagon, or might want to do something for the Department of Defense, or you might want to join the military, but the overwhelming majority of the folks in the United States will never get to, and a lot don't get a chance to join the military. So this fellowship gives a great opportunity for you to be able to work next to NASA and United Launch Alliance and Air Force Science and Technology and the different national labs and SOCOMs, Special Operations Command, Naval Special Warfare, a myriad of different organizations that you might just only read about in a book or movie or you hear mentioned on the news briefly. But our XForce Fellowship program, we engage with DoD partners. It's an opportunity for you to do a 3 to 6 month long fellowship or internship where you're actually working on national security problems. You could be attached to Peterson or Schriever or Buckley Air Force Base. We could fly you to the Pentagon. We could have you co-located at Fort Bragg. I'm mentioning locations where CU students were at this just last summer. And it gives them something tremendous because you're actually working on something. You're not, getting bagels and, getting snacks for the boss. You're actually working on actual problems. And if you're a coder, we might have you working on some new app that has something to do with something that I don't even know about yet. It's great. Great program, great opportunities for you. And the fellows, you guys, it brings some tremendous ability for you to build your network. It also looks great on your resume, and they're paid fellowships. So I mentioned the paid fellowships. You'll get about $2,500 a month. You also have a small budget for travel, for other expenses. The XForce Remote program is something that you can do here at school, and it's not paid, but the young lady who did this program, it looked amazing on her resume, and now she has her first internship or her first interview with the CIA. She learned so much from this program while she was in Washington. She was in Washington taking classes, networking there, and doing this program, and she's able to do a lot of networking and a lot of resume building and get a better understanding of what's happening in the outside world because she wanted to be in national security. So there's the XForce Remote program and the XForce Fellowship program. The fellowship program is paid, remote is not. Here's the dates. The reason why Dr. Curry let me come speak with you real quick is because I don't want the deadline to come and go, and by the time you come back in January, the applications are already full. I would want you to, the application date. The actual application is January 1st. Here's the rest of the dates. I can post this on the TCP website so we can get it for a later dissemination. But the ways that you can get involved in is on Handshake. Who here, raise your hand if you don't know what Handshake is. It's okay, we're a team, we should know. All right, one of the doctors, all right. Well, great, all of our students know. So follow it on Handshake. Here's the link for it. Here's our website at the INSA, National Security Innovation Network website. Go ahead and get some more information. You can go ahead and submit your intent. And my friend Joe, who is Joe Schumann, he runs this program in Washington, D.C., he's going to start compiling these, and then January 1st to January 31st, halfway through the time you guys are on break, we're going to pick however many spots we have, and I would love to I want to be stingy and selfish and get as many buffs into this cool program. I don't care about MIT or Georgia Tech or Stanford or the University for Spoiled Children. I want all my buffs on this program. That's USC, by the way. If you're from California, yeah, bad sense of humor. There's our instant website right there. I'm not expecting you to remember all this. I'm expecting you to say, oh, paid internship dealing with national security is going to look great on my website. As you are going to look great on my resume. I'm going to get some great networking. I'm going to learn more about something that I want to be passionate about. So Handshake, you should be on that anyway, looking for internships. These jobs aren't just going to fall out of the trees. You need to network your way into these and get experience. My email, rex, like the Colorado@colorado.edu. These are both, these two pictures represent two teams this summer where our buffs, we're buffing it up. And this is one of our young men right here. That's the Falcon Heavies behind him. He was in Florida. And then these folks right here at Bragg working with SOCOM S&T, working on some new way to, like a stretcher type system. So it doesn't have to be totally like technical. Questions?
Do you need a security clearance?
Great question. Do you need a security clearance? The answer is no. You're not going to be in the SCIF or where all the secret stuff happens. You might be housed outside the base. You could be on the base, but you won't be in an area that you need TS-SCI clearance. So it's if you're trying to get with the NSA or NGA or NRR or whoever, or want to get for Northrop Grumman or somebody, you're going to get clearance. The fact that you're working on these programs with the government is going to look great on your website, great on your resume. What other questions we got? Go.
Can international students apply?
Can international students apply? They can. Some areas are not, just like with anything, if it's a contracting organization. But go ahead and email me and we'll give you some specifics about some programs. There are some programs that we let our international students work on. If you are Russian or Chinese or North Korean, no. Don't even think about it. So, what other question we got? Question. Okay, I've got some business cards here. I didn't want to bring a flyer that's just going to get thrown away. I'd rather invest my time and money into a business card so I could be a resource to any of our TCP students as well for networking, job-related stuff. I bring about a myriad of other talents and Rolodex that I love offering in our students. If I can help any Dan or Dr. Curry or Keith or any of your students, even though you don't know what Handshake is, we'll talk about that later. We get them all spun up on Handshake. So, but I want to get out of Dodge. You guys have some learning to do about which I had to Google what was. So I'm going to turn this off. Thank you so much for your time.
So let's thank our speaker, please. I will get some of the slides posted on the website, if that's okay, Max?
Okay, sure.
It's available.
Yeah, it's all in class.
And there are a few cards up here, and I'll leave them at the end, and at the end, we will.
Oh, I should have.
Okay, good. So, our speaker today is Dr. Keith Gremban. Professor Gremban is a research professor here at the University of Colorado Boulder in technology, cybersecurity, and policy. Now, I first met Keith maybe 3 years ago and realized that there is an organization just across the street from the university called NIST, or National Institutes of Standards and Technology, and NTIA, National
Telecommunications and Information Administration.
Whatever he just said. And I was surprised because they worry about issues around spectrum and spectrum management. And I kept asking myself, why should I care about spectrum? What does it have to do with the future? Isn't it something that you see late at night in the northern parts of the world? Is that sort of what spectrum is about? And I think all of my information was completely wrong. And Professor Gremban is going to tell us about spectrum. Now, he has worked at CU Boulder for exactly 1 month. And so, please welcome Professor Keith Gremban to TCP again.
Thank you.
So, thank you.
Okay, so I'm going to probably cover all three of the areas here. You're going to start off with some policy stuff about how spectrum is managed and why and so on, and then work into some of the technical challenges of managing spectrum. Okay. Hello?
It's broken.
Okay, let's restart. It got bored waiting.
Oh, there we go. Macintosh machines actually perform much better.
My daughter works for Microsoft.
Oh,
Sorry, thank you.
Okay, so just to get everybody on the same page, and I'm sorry if this is repetitive for some of you, but typically in every audience there's a few people who don't understand the basic of spectrum and then they're lost through the rest of the talk. So spectrum is radio waves, and a wave is defined by wavelength or frequency. And so, wavelength is like peak to peak, and the frequency is the number of waves per second that travel past a different point. So if this is a 1 second interval, we've got a 2 hertz wave and a 9 hertz wave, where hertz is 1 wave per second. And then I'll be throwing around kilohertz, which is 1,000 waves, megahertz, 1,000,000 waves per second, gigahertz, 1,000,000,000 waves per second, and terahertz is 1,000,000,000,000. And so radio waves are from 30 to 300, from 30 megahertz to 300 gigahertz down here. You get up into the terahertz range, you're talking visible light. Important thing to remember, and kind of the basics that you really need to understand, is that the properties of the radio waves change depending on the frequency. And just the rough way to think about it is, the lower the frequency is, the better the wave penetrates obstacles and the farther it propagates. But because it's lower frequency, it has less capacity. You increase the frequency, you increase the bandwidth and capacity, but they're shorter waves, so they're more blocked by obstacles, they don't bend around obstacles, they don't propagate as far. So you've got this trade-off in any system of, do I go with low frequency and penetrate and propagate well, but low bandwidth, or do I do high frequency, which will give me the capacity, but then I've got propagation issues. So let's start with some spectrum management history. So 1901, Marconi broadcast the first transatlantic radio signal. And like many good inventors, he saw a very big business opportunity there and formed the Marconi Company and started putting radio transmitters on ships so he could handle ship-to-shore communication, because there were big issues with, a ship's out for a week, what's happening? What's going on? If they get in trouble, how do you know? And so he saw this as a big commercial opportunity and quickly took steps to monopolize the market. A lot of other people, just like any other invention, when something happens, everybody else jumps on the bandwagon. And so Marconi started this practice of, even though they were working with the same radio frequency spectrum, he wouldn't pass on messages from any ship that didn't have a Marconi transmitter on it, except in emergency conditions. He did compromise to that point. So 1910, the U.S. passed the Wireless Ship Act, which was really the very first radio regulation law. And it required any ocean-going vessel entering or leaving a U.S. port to have wireless equipment installed on it. And it also had this odd requirement that operators had to be certified. So, I mean, just imagine, huh? You just started radio transmissions and now you've already got a certification process. Then, so many people got interested in radio that the Secretary of Navy that same year actually wrote a formal memo to the president complaining that there were so many radio people using the radio waves that it was hindering the Navy. And in fact, they were having problems with jamming interference and people issuing false SOSs to watch Navy and Coast Guard ships go run out and do things. So that was a little bit of a concern, and then the big thing happened when the Titanic sank. And part of the problem was that the rescue efforts were hindered by this very problem of interference and too many people occupying too few frequencies. So as a result, the government passed the Radio Act of 1912. And this was the very first legislation that required radio stations to be licensed. It also made it illegal in the U.S. to not pass on not pass on radio waves that came from one particular manufacturer. It required interoperability between all the radio manufacturers. Okay, so then came the Radio Act of 1927, because again, radio is just propagating. And so much is happening that they had to do more in spectrum management. So they created this Federal Radio Commission within the Department of Commerce to manage, Federal spectrum management remained in the executive branch, but a Federal Radio Commission was established within the Department of Commerce that was for non-federal use. And they tried to now manage radio stations and so forth. And it turns out that they found that the Radio Act of 1927 was toothless. They had a few rogue radio stations that they tried to shut down, and the cases went to court, and they said, yeah, you can license them, but you've got no authority to shut anyone down. So that led to the Communications Act of 1934. That fixed that problem. That established the Federal Communications Commission to regulate commercial radio and gave them now the teeth to actually shut people down if they were transmitting illegally. Also, a very interesting little side note in the Communications Act of 1934 was it specifically stated that state and local law enforcement could not employ jamming devices, which is something that I got involved with last year at NTIA. Just kind of an interesting why. It's an old regulation. So federal use still is managed within the Department of Commerce. So then in 1978, just by executive order, not a legislative act, the president established NTIA, the National Telecommunications and Information Administration. And their job was to manage federal use of the radio spectrum, a job they're still doing today. Now, interestingly, since the dawn, up to this point, since the dawn of the radio age, licenses didn't cost anything. All you had to do was apply to the FCC for a license, and the criteria for granting a license was, did it promote the public good? And so if you had two companies that were both competing to get a license in the same metropolitan area, they had to go to great lengths to try to convince the FCC that I'm the one who can serve the public good the best. And it ended up with applications for licenses were thousands of pages thick. And it got enough it got enough attention from the companies that just didn't want to go to all this effort that the FCC said, okay, we'll try something else. oops, we'll auction off. We'll do a lottery for spectrum licenses. That way, everybody has the same chance. You don't have to produce these big stack of paper. Well, it's a lottery, and some people really hit the jackpot. So it turned out anybody could apply for a radio license. And so there were random people off the street that just said, what the heck, I'll apply for a radio license. And they got it, and then sold the rights for millions of dollars to a broadcaster. So it truly was a lottery. And so again, the FCC's going, no, this doesn't make sense either. This is a valuable commodity, so let's try selling it.
Is that sort of similar to what's happened with internet domain names and things like that? I mean, are we seeing parallel structure?
Yes and no. So there's a corporation that's responsible for internet domain names. They license the rights to that to companies like GoDaddy and so on that then sell them. And if you go on GoDaddy and see if a domain is already taken, and you come back a week later, odds are the price will have gone up on it. I have personal experience with that. So the first auction was done in 1994, and it was considered to be a pretty big success. And so then the most recent auction was in 2015, 65 megahertz, and it went for almost $45 billion that got added to the federal treasury. And I'll talk about this some more because there were complaints then that only the guys with deep pockets got to bid. And so what about the small guy that just wants to start a little cellular service in Eagle, Colorado or something? What do? And so I'll say more about that later. But that's kind of a brief history of spectrum regulation. And of course, when you've got regulation, you need organizations that have to regulate it. And just at the very top level, your objectives are to make efficient use of this resource and to minimize interference between licensees. And so radio waves have this interesting property that they don't really respect national borders. So there has to be an international organization to regulate it. So the UN created the ITU, the International Telecommunications Union, and they manage spectrum management across all the member states. And it's done through the mechanism of this World Radio Communications Conference, which was held every couple of years. And that is a big deal. WRC 19 just finished on November 22. It was a month-long conference in Egypt. The U.S. delegation is led by the State Department with support from every federal agency. And so this is where all the arguments are taken as to what spectrum is going to be reserved for what purpose. So within the U.S., as I said, the FCC, the Federal Communications Commission, manages commercial, state, local spectrum. It is a legislative branch organization, so it reports to Congress. It has a technological advisory council that consists of experts from the community, from outside the federal government, that advise them on new technology that's coming in and how it might have impact on spectrum management. And then the NTIA manages federal spectrum. It is an executive branch organization. It is within the Department of Commerce, and its official mission beyond managing federal spectrum is the primary advisor to the president on telecommunications policy. And they coordinate with other federal agencies through the mechanism of the IRAC, the Interdepartment Radio Advisory Committee. And then they also have their team of experts, the CSMAC, the Commerce Spectrum Management Advisory Committee, that is a group of non-governmental people that advise them, again, on new technologies, policy issues, and so on. By the way, if you have any questions, any point, ask me. So spectrum management, up until very, very recently, was a very top-down, what they call a command and control type of process, where decisions are made at the top and filtered down to the people that actually are influenced. And the two words you have to understand are allocation and assignment. So an allocation is a reservation of a block of frequencies for a specific use, like air defense radar or TV and so on. So just for example, all FM radios are allocated this frequencies between 88 and 108 megahertz. The terminal Doppler weather radars around airports are given 50 megahertz in the 5 gigahertz band. A spectrum assignment is where a licensing activity takes place, and it assigns a particular entity or organization the ability to use that frequency block in a particular geographic area. And a spectrum assignment includes things, not just the frequency, but the maximum power, the antenna height, and all the factors that influence the propagation of the radio waves. And so just for a couple of examples, you know, our local radios, 2 of our local TV stations are right next to each other. KWGN has 6 megahertz from 590 to 596. KCNC is the next 6 megahertz above that. And you can see they're pretty much the same power, but the antenna heights are different, and so on. I'll get back to some more details about that next.
Excuse me, do people really care about the antenna? I mean,
I will give you an example of why.
okay, sorry.
The antenna height is important because it determines the coverage area. So if you've been covering an area and you're not interfering with somebody and you double the height of your antenna, all of a sudden you can be causing interference. So this is the result of the command and control style of spectrum management. This is the official United States frequency allocation chart. It goes from 3 kilohertz up to 300 gigahertz and defines exactly what purpose each block of spectrum can be used for. This is maintained by the NTIA. Those of you who are really excited about this can go to the NTIA website and download a high-resolution PDF suitable for framing. So let's dive into details literally here. Let's look at what happens inside this block, which was used for that AWS-3 auction that raised $45 billion. I'll zoom up that part. Now you can almost read the words. So let's zoom in a little more. The AWS-3 band is this blinky area right in here. Remember, that's $45 billion. And when you build it up even more, you can see they carved out space operations and mobile and fixed and gave this block of spectrum out at an auction and raised
That little sliver of orange stuff costs
$45 billion. Yeah. This is not chump change. And even Hollywood finds spectrum to be really sexy stuff. So anybody watch Blacklist? Okay, this was a scene out of the Blacklist. The FBI was coming to get the bad guy. He was listening in on their communications, picked up his go bag, and ran to the door. And as he ran to the door, I went, "That's our chart!" and paused it and took a picture. So this is good stuff. So the heart of spectrum modeling, the heart of spectrum management depends on understanding radio frequency propagation. And to do that, you need computerized propagation models. That is the most important tool in spectrum management. And the reason is because you use these tools to predict what regions you're going to get acceptable reception and where you're going to overlap somebody else's coverage area and cause interference. And it's a complicated process because, as I said earlier, every frequency has unique characteristics. And you've got to cover the whole range of frequencies in that monster chart, which no model does yet. But this is what the FCC uses to evaluate coverage areas and license restrictions. So this is an example from a tool that ITS, the NTIA laboratory across the street, built called the Propagation Modeling website. It's used by other federal agencies. In fact, it is a mission-critical system for the National Weather Service, and ITS has to keep it online 24 hours a day, 7 days a week, because what it's used for is if there's a weather emergency, Congress requires that the special weather alerts that go across your screen reach over 90% of the affected population. So when they issue a weather alert, they have their transmission stations and they run the propagation algorithm to see what coverage area they're going to get out of that alert, and if it doesn't cover enough population, they pop up another transmitter. And so this was also used, so in the last couple of years, with the advent of digital TV, it allowed better TV transmission with less bandwidth. And so the FCC said, okay, we're going to take all these television bands and we're going to shrink them in half, and we're going to use this top half for cellular. And so they did what is called band repacking. And as part of the band repacking exercise, several of the television stations in the Denver area that have transmitters up on top of Lookout Mountain wanted to increase their power from 890 megahertz or 890 kilowatts to a megawatt. And to do that, they had to run this model and get the approval of FCC. And I actually got involved in that because NTIA, does everybody know Table Mountain north of Boulder? Big flat top place with the radio dishes on it. That turns out to be one of only 2 radio quiet zones in the entire United States, where the intensity of radio emissions is controlled by federal law. And so before they could raise the power of their antennas, they had to ensure that it wasn't going to interfere with operations on Table Mountain. And so we spent several weeks running lots of models with the FCC and trying to decide if it would. And in the end, it didn't, so they were able to increase the power. So demand for spectrum is exploding. You know, think of all the wireless devices you have now that you didn't have even 2 years ago, right? And they're not making any more spectrum. They stopped that process 13 billion years ago. So we gotta make do with what we got, even though these demands are just going nuts. You know, just if you don't even consider more devices, you know, we're just going from standard definition to high HD to 4K on your phone, which is going to require, again, a lot more capacity. So that chart that I showed just is not sustainable. There's no way to do it. We've got to come up with a way of sharing. And sharing takes place both in space, which we've been doing with different radio stations in different areas of the country, and time. So let's see how some of that works.
So did you just say that I may have spent $45 billion and then it may be worth significantly less in the next 4 years? Or
Oh no, it's only going to get more valuable. In fact, there's another auction I'll talk about in about 2 slides that's coming up. That'll be very interesting. So the first real attempt on large scale to share spectrum was the 5 gigahertz dynamic frequency selection process. And the idea here was, if you look at this particular band of radars, 5600 to 5650 was where they lie. It's terminal Doppler weather radars. They're only around airports, and they aren't even on all the time, right? They're only on when there's a threat of wind shear. And so the thought was, okay, that's a good band for Wi-Fi. Let's see if we can share it. So what are the requirements to share it? Well, the idea was that these devices, called UNIs for Unlicensed National Information Infrastructure, would listen for radar signals, and if they heard them, they wouldn't operate. And radars would always have override ability. Everything else had to work on a not to interfere basis. And so the thought was, okay, I'm a UNI device, I'm going to listen, I don't hear a radar operating, okay, I can use this. But the moment I hear a radar, I got to move and get out of its way. So these were the parameters it had to meet. It had to detect the radars at fairly low intensity. It had to abandon, well, before it used a channel, it had to listen for 60 seconds to see if a radar was spinning. And if it didn't hear anything for 60 seconds, then it could use it. If it heard a radar, it had to abandon that channel and couldn't use it again for at least 30 minutes. And if it heard a radar, it had to get out of Dodge within 10 seconds, which is pretty good. And it worked. So these devices hit the market about 2006. This was about 3 years after it had been discussed at the WRC-03. But to think about it, it was 10 years after the initial FCC report and order was developed. And then in 2009, they were starting to get reports of interference from the FAA in particular places, San Juan, Puerto Rico, New York City, which oddly enough are good ports for cruise ships. And the causes of interference were a couple. So first of all, they weren't properly detecting radars, and this was not the fault of the devices. This was the fault of the radar operators not telling NTIA all the characteristics of their radar that had to be tested for. So they said our radars operate like this. It turns out they also operated over here. And so the tests weren't designed to detect that.
These radars were owned by,
FAA.
and so FAA didn't communicate the information correctly.
Right. The operators did not understand their radars well enough. Then there was also this thing that because of these international agreements, it didn't work the same way in all countries. So when you set up one of these devices, you had a little drop-down menu and you picked the country that you were going to be operating in. Well, it didn't take cruise ship operators very long to realize that, if I use this country, I never get complaints from my customers. And so they would just set the country code to the most agreeable country, which ended up interfering in the United States.
So they would cheat.
They would cheat, yes. Then there was, of course, the problem of illegal transmitters and ones that were improperly deployed and modifications. And then, of course, the ultimate bugaboo of any computer-operated system, when you update it, did you break something? And it turns out they were. But these once identified, these things were dealt with, and this is working pretty successfully. But that was pretty simple stuff. And it still took 10 years to do. The next approach to sharing was the 3.5 gigahertz band. And this is going to be a much more sophisticated sharing in time, as well as addressing some of the licensing issues. And so in 2010, NTIA was given a presidential directive to find 500 megahertz of federal spectrum that could be repurposed for commercial use. And they did a real, what they called a fast-track report that identified 3.5 gigahertz as a really, really good place to repurpose. And I'll show why on the next slide. And so it had to be shared because there were federal incumbents, shipborne radars, radar test sites, satellite downlink stations, and actually a few cellular providers that were operating at that frequency. And so the catch really became, how do you coordinate all this? It wasn't too hard around these, which are fixed sites, because then you can just draw a geographic boundary and say you don't go inside there. But what do you do about these radars? Well, so they used propagation analysis to define these regions where they had to coordinate. And then they defined two systems, a spectrum access system that would each time perform an interference analysis and give permission to transmit, and this environmental sensing capability that would detect radars and tell people to turn off. So let me explain that more graphically. So the 3.5 gigahertz radars are shipborne radars. Go stand on top of a building and look around. There aren't a lot in Colorado or anywhere in the center of the US. So the telcos were, rubbing their palms going, all right, this is a great band for us to use because basically it's been empty for years. Okay, but the problem came, what about near the coastlines? And so in the fast track report, they did a very simple propagation model with basically smooth earth assumptions and so on, and got these huge, 70, 80, 100 mile corridors that they were going to say you couldn't use this band. The problem with that is over 50% of the US population is within 50 miles of a coastline, including some of the biggest cities in the US, between the biggest markets. So telcos weren't happy about that. NTIA then did another propagation analysis with an enhanced propagation model that took into account terrain and clutter and came up with these blue lines that reduced the size of these so-called, they were in exclusion zones, by almost 80%. And so then as the concept progressed, the idea would be, okay, they can operate anytime they want between these blue lines, but between the blue lines and the ocean, they've got to coordinate with the Navy. And so this was a very complex system of coordination. So they started off with 3 tiers of licenses. First tier was the incumbents, the Navy, the radar sites, and so on. These guys always have priority and get to override anyone else. Then there were the priority access licenses. And these are licenses that are going to be granted by competitive bidding. I think they're doing the pre-auction, and the auction is going to take place in the spring. And they can run whenever they want, except when one of these incumbents is operating. Then they've got to get out of Dodge and find another channel. And then they're doing this general authorized access, which is effectively unlicensed. And what's interesting is the highest 50 megahertz here, if you look at the priority access, is granted for this unlicensed realm. So this addressed that issue of the big boys getting all the toys. And so the way this works is the spectrum access system is a collection of distributed databases. And if I'm a telco and I want to, say, operate in Boulder, I send a message to the SAS and I say, I would like a grant to operate at this frequency in Boulder. And the spectrum access system has a database of all known transmitters that are using this band, and it runs propagation analyses, and it says, the next county over is using the same frequency, so unless you really power back, you can't use this. Or, okay, you're fine, you can use it, and you get a grant to use it. And the grants give you 10 megahertz at a time and gives you the maximum power that you're allowed to use, so you don't interfere with anybody else. But if there's any detection of a radar by one of these environmental sensors, the message goes out to everybody, turn out, get out of Dodge, change bands. And just in case a SAS would crash, they put in this heartbeat signal thing that every 5 minutes a SAS sends out a note to every one of its grantees saying, you're still good, you're still good. So if the SAS crashes, the default is you lose your grant and you got to turn off so you won't interfere with the radar. Yes, by the way, this is a air traffic control radar that operates off of carriers. And so it would be a very bad thing to jam that during the middle of a Navy air exercise. Bad things could happen. So the Navy was very, very worried about this.
Keith, I have a question.
Sure.
Is the SAS only for CBRS spectrum or for everything?
Just CBRS spectrum.
Thank you. I did not know that.
And I should say that ITS worked with the FCC and was the organization that developed all the test procedures and executed the test procedures to certify the SASs and the ESCs.
And one last question. The SAS is just in the United States, right?
Yes. This is as far as I know, this is a US only concept.
Got it. Thank you.
So all of this, as I said, depended on propagation models. Every time you ask for a grant, the SAS runs a propagation model. And so there's two propagation models that are used inside the SAS. The first is ITM, which is known in many communities as Longley Rice, and which was a development, again, at the labs across Boulder. Both Longley and Rice were ITS employees in the 60s. It's been largely validated with propagation measurements for benign, uncluttered terrain, but it doesn't take into account things like clutter, urban structures, and so on. So an urban model is the HADA model, or the extended HADA model, which was developed in the 80s, based on measurements of propagation in Tokyo taken in the 60s. You look at the pictures of Tokyo then and now, or you look at the pictures of Denver then and now, lot different profiles. But it's the best we had. It was extended by some NTIA people, and what it does is it says, okay, we classify this general property of an urban area, and in general, an urban area is going to attenuate radio frequencies to this degree. And it doesn't take into account things like, what's the actual geometry? What's the building material? Because you know, a suburban area of wooden buildings is going to have much different properties than a light industrial area of cement and steel. But that's not included in these. And these are conservative models in that they underestimate the loss and overestimate the coverage, which is good if you're trying to avoid interference. But the problem is, you also lose a lot with that. So here's a study that was done by ITS. So up here is the labs. This is Broadway here. And they put a transmitter up here and drove a sensor along this path. And you can see the intensity, the received power intensity is based on a color scale. So red shading to orange is high intensity, and as you shade to blue and purple, you're basically losing connectivity. And you see, okay, you get pretty good reception in the neighborhoods. And you come up here and all of a sudden you lose everything. And then you come down here, line of sight, you got really good reception and so on. And so if you take that path and you lay it out straight, you get this graph. Okay, so these purple spots are all the measured points. The black is a pure free space model, and the red is what the irregular terrain model would get you. And like I said, it's a conservative model. It way overestimates the propagation loss. And the problem is, if you're telling telcos they have to follow this line, all of this area here is lost commercial opportunity. So we got to get more accurate with these propagation models. So now this is my segue into 5G and millimeter wave. So as we're trending forward, the areas for spectral reuse are getting smaller and smaller, tighter and tighter. When we were dealing with broadcast radio and TV, we were talking hundreds of kilometers, and an error of kilometer was no big deal. Okay, now we're talking, neighborhood block size propagation. You can't have a kilometer of error if your block is 200 meters in diameter, right? So we got to do better. We got to get these prediction errors to be on the order of tens of meters. And when you're down at that level, this clutter, what we call clutter, foliage, building, billboards, other structures, now has a very important effect on the propagation. So obviously large urban structures like high-rise buildings will really have a big effect. But for millimeter wave, this clutter dominates. And we've got to understand it if we're going to be able to model millimeter wave. Again, in 5G, this outdoor to indoor transition is going to be huge. Down at the lower frequencies, what are called low band, under 6 gigahertz, not a big deal, right? I mean, you talk on your phone, you walk in the door of your house, you close the door, no big deal. Did you notice any difference? Millimeter wave, boom, you're done. Close the door, you're not going to hear anything. So we need to understand this. And then finally, which I've been talking to Jim about, the errors and uncertainty are very poorly quantified. We know that we can go out and stand in the same spot on 2 different days and get measurements that differ by 5 dB under what we think are the same conditions. We've had situations where a semi-truck drives by and we jump 6 dB in reception because of the reflection off the truck. So how do you quantify that and visualize it to somebody like working for the FCC that's trying to denote the size of these grant areas? And then finally, you get up in the millimeter wave regions, and the human body is impenetrable. So why does 5G care about millimeter wave if it's got all these problems? And the key is bandwidth. 5G is promising gigabit to 10 gigabit per second upload and download rates to mobile devices. You can't do that sub 6 gigahertz. You've got to be up in the tens to hundreds of gigahertz to be able to do that. But again, I keep emphasizing this. You go up that high, you've got very different propagation properties. Essentially at about the 1 or 2 gigahertz mark, you stop seeing so much wave behavior out of your radio waves, and you see they act much more like just light rays. They don't penetrate obstacles well. There's absorption by water, oxygen, and so on, as well as just scattering by dust and rain. So in general, this propagation is going to cause challenges. And in fact, industry estimates are that if you wanted to cover the same area with millimeter wave that you do with sub 6G, you're going to need 10 times the number of cell towers, which is a problem. So I'm going to go through each of these issues here, the geometry, the diffraction, the obstacles, and the absorption, and tell you a little bit about the properties of each of these. And what's interesting is, in trying to look up references that I could pull graphs and stuff out of, it reaffirmed my understanding that no 2 labs do the same thing, and it's very hard to try to compare results from different laboratories. It's a wild west in terms of how you deal with these propagation properties. And that's one of the things the community needs is standards for how to do these measurements and what data you're obtaining so you can share and compare it. So let's just talk about the diffraction. To me, the best work I've been able to find in this area is done by Ted Rappaport and his team at NYU. They just have done some amazingly detailed work. And they got interested in this problem of, what happens to diffraction at millimeter wave frequencies. And so they set up an experiment where they had a directional transmitter pointed directly at a corner of a building, and then they had a directional receiver pointed at the same corner, and they moved the receiver across the track so that they could measure the propagation loss from that. And so these are just a couple of the sample results. And so green is 10 gigahertz, red is 20 gigahertz, and blue is 26 gigahertz. And propagation loss goes up as you go up the x-axis. And the angle is on the the angle is on the x-axis and propagation loss is on the y-axis. And so you can clearly see, especially in this lower figure, that as you increase in frequency, you're getting more and more propagation loss. And they've characterized it very well in this study. Can anybody tell me why this looks like it does? That's because it's a directional receiver and it's still pointing at the corner. Even though it's up here, it's still pointing at that corner. So it's only catching reflections. It's not getting anywhere a direct beam. But the point is, you're getting 6 dB of propagation loss at just over a 45-degree angle. Wow, you're talking big shadows around buildings. Propagation indoor is a problem. And the team at ITS did some work at 2015 here over at the DCL, where they put 2 transmitters in the TPC lab at the end of level 1B, and then walked around in a ring around each corridor and measured the propagation loss. And so again, we've got this, this time we've inverted. So red means very poor reception and blue means good reception. And so you've got very good reception down this corridor. You start losing it as you get farther and farther away, and you start building it up again until you're finally back at normal. So can anybody tell me why, just from your experience, why there would be good reception on one corridor and not the other?
So you said 1B level?
Yes. In the conference room I went to thinking that was where I was giving the seminar.
1B70. Got windows.
No?
No?
What's this wall?
Concrete. Yeah.
It's all metal. Got a big metal screen on that wall.
Yes, you're right.
I know.
Propagates north to south.
Yeah. So I walked over there this afternoon to take a look at that and go, that doesn't make sense. Why is that true? And I saw that metal screen and went, okay, we got it.
And of course, the designers of the building never thought about the issues of propagation indoors. Right?
No. Who would have thought of it then? And so then outdoor propagation also has some interesting characteristics. We did the same thing. We put a cell tower up on Green Mountain, about 2 miles that away, and measured on a walking path around the building. And so you can see the effect of the building. Here we've got good reception, and this is almost directly on a line with the transmitter. And you get over here to where the building is shadowing it, you've effectively got one big dropout area. And this is with at 700 megahertz, which is a pretty good penetrating frequency. Outdoor to indoor is even worse. Same thing, and I went to level 2 because any of the levels below there was effectively no reception whatsoever because the walls were just stopping it. And it turns out, by the way, they discovered in doing this work here that LEED buildings, LEED is it? The ecologically friendly buildings.
LEED.
LEED? Yeah, there. Thank you. They're terrible for RF penetration. Those nice shiny windows that reflect light, they also reflect radio waves. So that can be a problem. And then here's the results that Rappaport got on the human body. So what he did is set up a transmitter and receiver 4.5 meters apart, and then had a test subject. And if you're interested in reading the paper, it's got the height, the width, the weight, and so on of the test subject. And at half-meter intervals, he would just walk between the transmitter and receiver at 9 different locations. So 1, 2, 3, up to 9. And so what you can see is at location 1, he gets right in front of the transmitter and cuts it off. There's no signal getting through to the receiver. As he moves out further and gets like right into the middle here, now you're getting more power over to the transmitter because there's more diffraction around the body. But you get into, again, walking right in front of the receiver, you've completely cut out reception. So this is important in the millimeter wave because the telcos all recognize millimeter waves has propagation problems. And so probably the initial deployment of millimeter wave 5G is going to be in things like factories and warehouses where they've got a controlled environment and they can set up transmitters to ensure coverage of all the areas. But what this is also pointing out is that you can't just think about fixed obstacles. You've got to think about planning those transmitters to deal with mobile obstacles. So you probably want them up high, going down, so people won't walk in front of them. And then I mentioned atmospherics. This is part of why you're not going to get good coverage. So millimeter wave, so we've got frequencies starting at 10 gigahertz, going up to 400 gigahertz, and you've got attenuation or propagation loss going up on the vertical axis here. And you can just see there's huge areas where oxygen and water molecules basically absorb all the millimeter wave transmission. So it's going to be a challenge to get this working outdoor. So what's the point? So spectrum sharing is the future. Some would say it's the present of spectrum management because there's just not enough spectrum to go around. Oh, I put a funny on this one. Human body's impenetrable, you make a better door than a window. Sorry. So sharing regions are getting smaller and smaller in both space and time. And when we hit the 5G millimeter wave, it's going to be, like I said, neighborhood-sized areas, cell towers that cover a warehouse, and if they're sharing, it's going to be sharing on a very dynamic level, almost like Wi-Fi. I hope I got you thinking a little bit about what's the fairest way to assign spectrum, because I'm not sure we've got the answer to that yet. But the thing I really want to leave you with is propagation models are essential tools. They're absolutely critical for determining coverage and interference, but they are not up to the task of millimeter wave yet. So let me leave you with some research challenges. Number one in my mind is we've got to improve the accuracy and resolution of propagation models. They just do not have the accuracy we need to minimize the coverage areas. One of the things that we can do, think about this, the Longley Rice model was built in the 60s. It's an irregular terrain model. Do you know how they got their terrain? They went on a topo map and a ruler and wrote down the altitude of different points along a straight line because there wasn't any digital data.
But now they can look down from space and get relatively good.
Well, yeah, not only that, I mean, so Boulder County is in some sense, very lucky. When the floods hit a couple years ago, the U.S. Army Corps of Engineers came in and built a sub-meter resolution LiDAR map of the entire county. That data is available.
Research project.
There is also available for national security research. DHS maintains a database called DHS Gold, which has sub-meter resolution digital maps of the 40 biggest metropolitan areas in the United States. And so now, we didn't have this stuff when we were first creating models. I mean, you look at an old topo map and say, okay, there's a building there. Okay, go out and drive around. It looks like it's about 20 feet high, so I add this 20 feet to my model. And now we've got all that digitally. We can get at it. We can know exactly what the geometry of these things are. And if you go through like a Google Map type or Google Earth type thing, we get a good idea of what the building materials are. So we could really develop good propagation models that take account of geometry and building materials. We really need to extend the frequency range. Right now, ITM is only good up to about 30 gigahertz. And at that point, the the propagation properties change so much that the package just isn't able to cope with it. I mentioned this before, we need standards for experimentation and data collection. It is right now not possible for two labs to go out and make the same set of measurements and be able to share their data and collaborate on it.
What do you mean it's not possible?
They bring things in different formats, they set the experiment up differently. This became such a big problem. There's a US Army program called SSTD, Spectrum Sharing Test and Demonstration. And they had a whole horde of contractors go out and make measurements and found out they couldn't use them together because they didn't have the same metadata. They didn't, there were these hidden assumptions that you do whenever you make an experiment. They weren't written down, so nobody knew what they were. They couldn't compare it. And so SSTD actually had ITS write a pretty thick document on best practices for RF measurement to try to standardize the way this would be done. And you need that because it's critical to perform model validation. There's a bunch of RF propagation packages out there that say we implement the XYZ theoretical model. Okay, is that the right model for this situation? In the Rappaport paper, he compares 3 different models and finds that each one is good for a different one of these situations. Okay, we need to validate it. Another thing that's very important to me is algorithms to quantify and visualize uncertainty. We know there's going to be uncertainty. Just wind blowing is going to change, the measurement by a couple of dB. So how do we, produce a package that somebody at the FCC, who's probably a lawyer, not an engineer, can, run a propagation model and say, oh, okay, then if I'm going to accept this amount of risk, this is where I'll cut it off because this is where the uncertainty grows too high. We don't have the tools to model that and present that to people. Again, these propagation models are, for the most part, pretty old. They really aren't using modern computational methods, which, as a computer scientist, kills me. And then the human-machine interface. One of the standard propagation models used by the FAA is characterized as user-hostile. And we need to fix these things. We need to make this stuff get into the realm of the everyday person, not the specialized RF engineer. Okay, so that's all I had prepared. Questions, comments?
So let's thank our speaker, please. Because of the time, we have time for a couple of questions. Who wants to go first or second or third?
I'll ask a question. What was the impetus for the Carter administration to stand up the NTIA?
I have no idea.
I don't either.
I'm sorry, I have no idea.
I was 18 at that time, and I couldn't remember what triggered the Carter administration to do that. So somebody else with the question.
So why is it the case that the models are so bad? I mean, in '60, they developed something. Shortly afterwards, they developed the HANA model. Why doesn't anybody just think about this as an interesting research topic and then run off and create 4 businesses or something? I mean,
So there are a number of businesses that have commercial propagation models, and we can argue about how good those models are. But, up until recently, the models were good enough. Okay, it's just, the technology curve just went boom, while the modeling curve was staying straight.
Yep.
And so it's just, all of a sudden, everybody's looking around going, wait a minute, what happened? And, I'd like to kind of get more people involved in this and make some breakthroughs in this area, because I think it's really important.
But it seems like a huge set of opportunities. I mean, you quantify the uncertainty, you build a model using faster numerical blah, blah, blah techniques, you incorporate the data, and so, and now the prediction model jump an order of magnitude in efficiency.
But it also takes a lot of work and requires a lot of expensive equipment to go out and do the measurements.
And people time.
And people time.
And who's going to pay for it?
Right.
Okay, good. So, other questions? I need up 2. Yes, a hand in the back.
Last year we had someone come in and talk to us about radar, and this is bad. And my question still has yet to be answered, which is that What's to stop people going out there? Because radar, immediately when you turn on any kind of radar or radio device, lights up like a beacon, and you can't see it. So what are the legal ramifications of jamming radar using a radio transmitter?
So jamming is illegal.
But if you're transmitting, are you considered to be jamming?
Yes, yes, yes. And in fact, the FAA has a collection of interference hunters that will go out when there's periodic interference to an FAA radar. They'll send people out to hunt for it. I was at a conference where the head of that organization at the FAA was talking about some of it. And some of the stories are just amazing. I mean, there was one airport that was getting interference at a particular time of the morning. And it turns out they tracked it down to this one house and they investigated it, and it was an amateur electronics buff who had taken a couple of old alarm clocks and soldered things together to make a new digital alarm clock. And when the alarm went off, it had an out-of-band transmission that would knock out the radar. I'm serious. They asked the guy, what do you want to do about it? And he took it off the stand and went, stomp! Similarly, there's, there GPS jammers are used, people in the trucking industry sometimes use their GPS jammers so their bosses don't know where they're going. And those can knock out GPS near an airport, which is again needed for terminal runway approach. So it's illegal, and sort of my take on this is for many, many years, building that kind of device was out of the the skill area of most individuals, but that's changing, and so that's going to be becoming an increasingly more of a problem, and there are some government organizations that are working on that because they recognize that's happening, or has the potential to be happening. And by the way, just as an interesting trivial fact, when Putin is traveling around Russia, you can almost track his route by the GPS jamming patterns. Because wherever he goes, they put on GPS jammers so we can't drop a JDAM on his head.
But then by inference, you have a sense of where he is.
A big sense. The CEP, circular air probable, is very large. I'm sorry, you had a question?
At the Spectrum conference that they did for silicon flat irons, they talked, at the very end, they started talking about how, yes, the small 5G waves are very, very small and they don't go through buildings and that's a problem. But no one's talking about all the other medium and long range 5G waves. Are those potentially a solution in cities, or is
So
I don't know what my question is, but there you go.
yeah, so to get the high capacity, you need the short waves, and those have all the propagation problems. And you're not going to use millimeter wave to cover, eastern Colorado or most of central Nevada, which is where I grew up. There's a lot of nothing there. And so for that, you're going to go down to the sub 10 gigahertz. And that's got much longer transmission, but you're just not going to get the bandwidth.
The data
It's a trade.
Yeah, that's a good question.
It's physics. It's just, you get coverage, you get capacity. You don't get both.
So on that note, let's thank our speaker. And I want to thank all of you for technology, cybersecurity, and policy for a very interesting semester. All of you have made fantastic progress. You write things, etc. And hopefully we will see you all next semester. And thank you. Yes?
So we don't need to show up to the final?
There is no final in this course. What I will do, if you wish, is open up the portal so that you can submit all of the projects that you may have missed. And most people miss one or two, and you get to decide if that's going to affect your grade or not.
Are you going to grade anything before the final?
The answer is no, I will not, but after the final I will be busy because I will have an accumulated sense of your data or your projects, and then I'll look very carefully. And there were some number of group projects, and some people turned them in, and so I have to go through and sort who did project X, or this group did it, only one was submitted, or 5 people submitted, and they have these red blocks, and okay, I understand. So there's going to be mix and match. unless people messed up, I expect most of you to pass this course, at least. Hopefully, please don't mess up. I have no time for that. So, again, thank you all for coming.
Does that mean we will not meet here at this time next week?
Correct.